Okay, so we are going to talk about first order linear differential equations. So we talked about when we did Euler's method that there are some differential equations that we can't use separation of variables on. And so Euler's method was nice because we could kind of follow the tangent line a little bit closer, even if we couldn't get the exact approximation, right? Our slope fields gave us an idea of what a general curve was going to look like, even if we couldn't find the equation of a general solution because we couldn't separate our variables. Okay? Now I'm going to give you a strategy only when it looks in a certain form, okay? If it follows this form, we're going to be able to find the solution, even if we can't separate our variables, okay? So we're going to look at just the first order linear differential equations. Mouthful. Okay? This is standard form. We're going to have dy dx plus a function times y equals another function. What is important about P and Q is that they are continuous functions. If they're not continuous, we can't do this. Okay, you can notice right now that separating our variables is not going to be an option.
Do they have to be differentiable functions? Differential functions.
They have to be continuous.
Okay.
So, as long as they're continuous, that's all we care about. Okay, so I'm going to tell you right now, much like the logistic work that we did, we're going to take a lot of time setting up the rule, so you understand where all of these random letters and symbols are coming from, and then we'll work through some examples with what we get through, okay? So, first of all, we're going to choose a third function, u, to be our integrating factor, okay? We can't integrate this right now, so we need some help. Okay, and we're going to strategically choose it where u times p is going to be u prime. Well, yeah, you don't know, you've never heard an integrating factor. Basically, we're going to multiply something so that we can integrate. That's what we're doing. Okay. Right now, things seem kind of wacky. It'll all come together as we start putting pieces together, okay? So, basically, we're going to choose an integrating factor so that we're going to multiply our entire differential equation by that integrating factor. So we are going to multiply u of x times everything, okay?
And with the equation you have above, could you also just say p of x equal to u prime of x over u of x?
We'll just wait on that, okay? There's a reason I have it written the way that it is.
Okay.
you to take a hard look at this right here. This is a pattern that you should maybe be able to recognize. Keep in mind, u prime is u of x times p of x. Oh.
The equation with y, that is the derivative. So it's y u prime x.
This is the product of u times y, right? U times the derivative of y plus y times the derivative of u. Okay, so this is the product rule if we were taking the derivative of u times y. Remember, u times p is u prime, and so u times p is our u prime for our product.
Isn't that like 3 different factor products though? Because p of x times u.
Well, okay. Let me maybe do this for you. Since p times u is u prime, this is like u times u prime of x, and this is u of x times y prime. Does that make more sense?
Yeah.
Like we defined u prime to be u times p, so it's not. That's not a product. Is that more clear?
Mm-hmm.
Okay. Okay. So now we can integrate. Well, okay. So when we integrate this, we get u of x times y, and over here we're going to get q of x, u of x, dx. If we were looking for y, could we solve for y at this point?
Yes.
If we knew our functions, right, we could integrate that right side and then divide u of x over and solve for y, something we couldn't do earlier. Okay?
Yes, so you should have something in the interval.
Is that supposed to be, in the integral, is that supposed to be dy over dx, or am I missing something? Why is it just d over dx?
It's just saying that.
It's just, this is representing the derivative of this product.
Why don't you divide the u of x over, but keep that side equal?
We will, when we actually solve these, we will divide that over. I'm going to leave it like that for now.
Is there any benefit to that?
Well, just so you don't get it mixed up in your, and I mean, it's going to be a function. You don't really want it a part of your integral. You want to do the integral separate from dividing that over.
Okay.
Okay. Okay. Now, let's come back to that integrating factor. Okay. We need to know what these functions are. Right now, I'm just throwing out random letters, it feels like, right? Okay. So how do we choose our integrating factor? We know that this needs to be true so that all of this will work out. Okay. Well, how do we make that true? Okay. Well, let's figure it out. You agree that p of x is u prime over u. U prime over u.
It's the reverse of it.
Do we have any sort of derivative rule that gives us u prime over u? It is the log. Okay, so this is the same thing as taking the derivative of the natural log of u of x. Huh? If we take the antiderivative of both sides with respect to x, then we get the natural log of u of x plus c on that right side. Okay. Now, if we need to know what u of x is, right? U of x is our integrating factor. That's the function that we need to make everything work in order to be able to solve for y in our differential equation. So this is our golden ticket right here. Okay? So if we wanted to solve for u of x, then we would have to move that plus c to the other side. It's a constant, so you can say minus c, you can say plus c, it doesn't matter, right? And then we can solve by rewriting this e to the left side equals u of x. We know that if we have e to something plus c, we know that constant can come out in front. Okay. However, since we are multiplying both sides by u of x, okay, that constant is going to end up canceling out, so we don't have to worry about it. So our integrating factor, u of x, we really just need to take e to the integral of p of x dx. And this is your golden ticket to solve these problems. Okay.
I would believe you, except there's a Q.
There is a p way up here. Okay. So, these are your steps. Okay, let's bring it all together. Okay? We just set up the groundwork so you're understanding what the heck is going on when we actually do this. Okay? First thing, you're going to make sure it's in standard form. So you want your derivative plus a function times y equals another function. It has to be in that form before you can go forward with any of the gibberish that we just wrote down. Okay? Okay. Then using that function multiplied to y, you're going to find your integrating factor. Then the whole point of all that, remember we multiplied everything by u of x. You'll rewrite your product rule and then go through the integration. So you're basically gonna go through what we did on that first slide, but with actual functions. Go through two examples together. You ready? Same as Mr. Holland sent me an email or
Mr. Coleman wasn't inside yet, so Mr. Johnson said that he was sending it, and what the entire staff sending guarded late.
we figured that's what would be happening. I'm recording this just in case. All right, Bailey, you good? Okay. First example. Okay. Is this in standard form? Okay. First of all, we need to recognize that we can't separate the variables, right? That should be something that you can recognize just by looking at that. There's not going to be a way to separate the y from the x because dy dx is being added or subtracted to something with a y. Okay? So, how do we get this into standard form?
Divide everything by.
Yep, divide everything by x. Whatever's multiplied to dy dx, we don't want it there. Okay? So, I'm going to go ahead and write this as dy dx. Okay? Minus, we have 2 over x times y equals x at this point, right? Okay, so that was our first step. We have rewritten it to standard form. Okay. Our second step was to do what?
Identify the integrating factor.
Find the integrating factor, okay? We know our integrating factor, u of x equals e to the integral of p of x dx. What function is p of x?
Negative 2 for x.
Whatever's multiplied to the y is your p of x. Okay? So, we have e to the integral of 2 over x dx.
Which you rewrite.
Would it be negative?
Yes, it would be. Good catch.
Oh, yeah.
It would be negative. The antiderivative of negative 2 over x.
Negative 2 natural log of x. Natural log of the absolute value of x.
Mm-hmm.
Plus c.
Remember, we don't have to worry about the plus c. Because, because it would carry down to here, right?
Yeah.
When we multiply by both sides, by the integrating factor, those constants are going to end up canceling out. So we don't have to worry about it in this step. It's just an extra thing that, since we know they're going to cancel out, we don't have to worry about writing it.
Never mind, I'll talk about it later.
Okay. So now, we have an e raised to something with a natural log. We could potentially simplify this, don't you agree?
Actually.
Potentially, let's try it. This becomes x to the negative second inside, right? Whatever's multiplied becomes an exponent. E to the natural log, those are inverses. So really we're just left with 1 over x squared as our integrating factor. Okay. The purpose of our integrating factor was to do what with it?
Rewrite the product rule.
Well, but first you have to take our standard form, dy dx minus 2 over x times y equals x. And we need to multiply both sides by 1 over x squared. So we get 1 over x squared times dy dx.
Oh, it's a little squiggly lines below the 1 over x squared over there.
That was just me kind of like highlighting this was our integrating factor. Because we had a lot of work, I was just highlighting that's what we ended at. If it confuses you, that's fine.
No, it's fine, we're still learning.
Okay? At this point, you need to recognize that this is the product rule. That was the whole purpose of choosing the integrating factor that we did.
Why did you?
Oh, thank you. I was getting, better? I got distracted with, I don't know what I got distracted with.
You got excited about that.
I did. Writing and talking is sometimes difficult to do. I know.
Okay, so it would be y over x squared. Would be integrative.
Okay, so we're taking, this is the product rule for y times 1 over x squared. Is that what you said?
Yeah.
Do you agree with John? That's the product rule for y times 1 over x squared. And maybe we want to write it like that.
What is happening to the 1 over x squared?
So, okay, if we look from here to here, this, if we took the derivative of y times 1 over x squared, we would use the product rule and we would get this. That's what we need to take. Okay? And check yourself. Write what you think the product rule is, and then see if it actually matches with what's in the above step. Okay? Now, what do we get to do? Okay, so our fifth step is to integrate and solve for y. So, when we integrate here, y times 1 over x squared. Over here, natural log of x plus c.
And this one doesn't cancel out, right?
This one we can keep.
Okay.
We can solve for y. And here is our general solution to the differential equation. Ta-da! Uh-huh. Okay, we'll do another example. You'll have time to start your homework. You'll have the weekend to finish your homework. Really, you need practice, okay? You're going to have to practice these. Once you get the steps down, it's really not that bad, okay? It's not that bad.
Pardon my skepticism.
Don't be. Don't be.
Your skepticism is not important.
Okay? But you have reached a point in math where I know some of you didn't have great study habits back in pre-calculus, right? I could get by with that studying, and for some of you, maybe you could, okay? This might not be a topic that you can just say, I don't have to do my homework. I don't need to study. You probably should practice and study, okay?
Could you add dy over divided by dx and then have dy dx equals? So why would you?
You were.
Is y plus 1.
Okay, so yes, you can add dy over and divide by dx, where you have y plus 1 cosine of x equals, hold on, yes, dy dx. Right?
Hold on. Did you have 1 over y plus 1 dy, and then multiply the cosine by dx?
Cosine dx equals 1 over y plus 1 dy.
Dy over
Second degree.
yeah, something we can do.
Well, should we see if we get to the same place?
Should we? Okay, I'll do the separation variables and we'll see if it matches.
I mean, you said first is to,
Let me pause it real quick.
you said the first thing is to recognize that.
It is the first thing. You are right. Okay, so use separation of variables and solve this one. What do you have?
Y equals c e to the sine x minus 1. Oh, not to it.
Yeah.
What do you say?
We don't see. Don't have this multiplication.
No, we don't have an explanation.
Yeah.
Do we have it in the other one? Or like, okay.
All right. Good catch, Bailey.
What's that catch? We work together.
You were piggybacking. Let's do this one then.
What's that extra? There you go. That'd be that idea.
Plus 2xy equals 6x cubed is standard, yes.
Well, you are right where you do need to add that 6x cubed over,
So divide by x squared.
but then you will have to divide by that x squared because you want dy dx to be by itself. So you will have dy dx plus 2 over x times y equals 6 over x. So it's going to be pretty similar to what we just did, isn't it?
Is that minus 6x? Is that minus 6x cubed?
Okay.
We gonna be 6x and 6 x.
Wait, what? No, you run by
Ah.
experience.
You got excited on that for us.
Okay, that is not similar to our other one. We're good. Okay, we all agree now. Okay, so now our integrating factor. We take e to the integral of
2 over x.
it is similar to our last.
It's almost a clone. It's just, and then it just has a 6.
I picked a random problem that was too similar to the one we just did. You wanna keep going?
Sure.
Even though it's gonna be similar?
Sure.
Find the hard one.
Okay.
The worst one you can find.
Oh god,
And then you'll only get better from there.
So this is e to the 2 natural log of x. Right?
Wait. Addition is addition 2.
So x squared is our integrating factor.
I feel like we just undid what we did to standardize.
We're multiplying by x squared, isn't that what we just divided by?
You're literally back to square 2.
And we're going to multiply our standard form. Multiply by our integrating factor. So we have x squared dy dx. 2x plus 2xy equals 6xb.
X squared 1.
So this addition is the product rule for x squared times y. Is that what you said? Yeah?
This is rather similar to your sheet.
It seems what?
Just feelings of deja vu.
I know. I was picking a random problem, then I with it.
No, I'm talking about the other problem.
Okay, so now we'll integrate x squared y equals 6x cubed, no, x to the 4th divided by 4 times 6 plus c. And then to solve for y, we would have to divide by x squared. So I would probably write this as 3/2 x squared plus c over x squared. That's probably how I would write it. Yeah.
Where'd you get x squared times y?
When we get to this point, when we multiply by our integrating factor, we have to figure out what the product rule is. Okay, so we need to figure out what two functions multiply together to where when you take the derivative, this is their product rule. So we have x squared times y prime plus 2x times y. So that's the product rule for if we would take the derivative of x squared times y. Does that make sense?
Yes.
Okay. This is your homework. We accidentally did 2 problems that were similar. Do you want to do a different one or do you want to start your homework? Okay. Huh?
Never mind.
Sorry, I did. Continue.
Oh, never mind.